Hi, this is Sahithi. Today, me and my team will be talking about Lab 5 for EE542, wherein we are modifying the TCP/IP kernel. To talk about TCP, we have acknowledgement and backoff mechanisms, which are used for congestion control. But TCP cannot differentiate between packet loss due to congestion in the network and the packet loss which occurs due to an unreliable link. So when we have a case of unreliable link, that is a lossy link with high latency, the congestion control mechanisms that we have in place for TCP are not quite useful. So in this lab, we are basically trying to modify the TCP stack and build the new kernel. And we are going to check how the file transfer protocol, which is SCP, uh, improves in speed. This uses TCP, so we are trying to modify the TCP stack. So first, I'll show the steps that are used in order to get the TCP files. First thing is that we have to clone this particular repository using Git. And after that, we need to execute this command and we need to go to sources.list and uncomment all the lines which start with deb source. And only if we do this, the next commands will work. After that, we are going to install the libraries using the commands given here. And after this step, we need to choose the version which is closest to our AWS version. This can be done using git tag. So when we do git tag, we get the list of all the versions that are available, and we pick up the version which is closest to our AWS version. And then we do a git checkout. And once this is done, we'll have the files, and we have to make the necessary changes to those files. And once the changes are done, we are going to follow the second method here, which is given for incremental build, and we build the new kernel, and this generates images, which can be seen here. These are the images that are generated. And using these images, we transfer these images to the client and the server, both on the VM and AWS as well. And we bootload this kernel, and then we execute all the test commands that are required. So this is a brief overview of the process that we have followed. So firstly, I'll be talking about TCP Vino. And here, as you can see, the first change that we have done is we are incrementing the congestion window by a higher value. Earlier, it was being incremented by 1. Right now, we are incrementing it by 3. The next change is that we return the maximum congestion window size, which is SND underscore CWND underscore clamp. So this holds the maximum value all the time. The next one is here again, we are returning the maximum congestion window size. So this is the change. These are the changes for TCP Vino. Next, coming to TCP timer.c. The first change is that we are increasing the timeout value and we are modifying it to be 2.1 into RTO base. And here we are basically trying to comment the backoff mechanism that we have here. The next change is that we are not updating the timeout value, and we are keeping it constant. That is the value that we have mentioned here. Here, we are not updating these values. We have commented this, that is, we are not picking up the minimum value here. Similarly, we have commented this as well. Here, we are updating the backoff and the retransmit values to constants. As you can see, the backoff is updated to 5 and the retransmit is updated to 2. And we have commented the parts wherein each time it was just updating by 1. Here, for the timeout value, we are picking up the maximum value directly, and we are not looking for the minimum of the two. Similarly, here, we are doing the same thing. So these are the changes in TCP timer. Next, we'll go to the changes in TCP output.c. So the first change is that we choose the maximum value, and this is available in the restart congestion window variable. Next, here also for the congestion window size, we choose the maximum value, which is available in clamp. Here, instead of choosing the minimum value for space, we choose maximum of two values, that is maximum among window clamp and space. Here, we change the receiver window size to the maximum allowed TCP window size, which is available in this variable. Next, we directly take the window clamp value instead of going for the minimum value. Here we are again taking the maximum window size in the new window. Again, the same change here as well. Here, here the new window value is being updated, so we don't want to do that. So we retain the same value that we have before. Here, we are not updating MSS to the minimum value. We are retaining it to the same value. Here, when we set the limit, we are not taking minimum of the sender window and the congestion window. We are only keeping it to sender window size. Next, here we are not reducing the congestion window size. So we have commented that part here. Here we are not updating the slow start threshold value, and we are keeping it to the minimum value, that is the initial value that we had. Next, we are retaining the window value as well, and we are not updating it. Here, we are using the maximum window size that we have instead of choosing the minimum of the two. And here, the segment size, we are retaining it instead of picking up the minimum value. So these are the changes. And next we'll go to TCP underscore minisocks.c. Here we have done only one change, that is we are using maximum congestion window value, which is available in clamp. The next changes are in TCP input. So here we are keeping this to the maximum value. So the same thing is being done here. And then for the buffer, we are using write memory instead of taking the minimum value. And here we are not dividing the window by half, and we are maintaining it at the threshold value. And next here we are using the maximum value, which is available in clamp, and not using the minimum one. Here again, it's the same thing. We are using the maximum value. Here again, we are returning the maximum value, which is available in clamp. Here also, instead of setting the congestion window to 1, we are setting it to the maximum value, which is available in clamp. The same change has been done here as well. We are just setting the congestion window size. So all these changes that we are doing is to basically make sure that the window size is intact and it's not reduced when we see when we see that there are no acknowledgements obtained by the sender. And also we are getting rid of the back of algorithm because as we discussed, both of these mechanisms are not really suitable for lossy links which have high latency.
Hi, this is Ananya. Now I'll be talking about the changes that we have made in TCP Hybla. So first, I'll be discussing about the changes made in TCP.h. So here we have first changed the maximum window size. Basically, we have doubled the window size. The next change is we have changed the threshold. That is basically it takes TCP takes 3 duplicate acknowledgements, and now we have changed it to 1. The next change is here where we have changed the number of retries, that is from 6 to 5. We have reduced it. The next change is we have modified the RTO according to the paper that we have read. Here the next change we can see that is basically scaling the window, and the scaling window has been changed from 3 to 6 in this case. And we have turned off Naggle. Next, I'll be talking about the changes made in TCP Hybla. So here the first change is we have reduced the congestion window from 2 to 1. And I have changed the sender congestion window to a maximum, not the minimum. The sender congestion window is set to the sender's clamp window, not the minimum, but the clamp size. Next, I'll be showing the changes that we have made in TCP Kong.c. Here, the main change we have done is setting the sender's congestion window to the clamp. And then we have changed the maximum, that is, we have returned the same sender congestion window here. Next, I'll be showing the changes that is made in TCP.c. So here we have removed the timeout. So this is where we disable the backoff algorithm. So here we have done the same thing, again removed the timeout. The next change that we have done is we are setting the congestion window to initial congestion window instead of 0. And the next change is the sender congestion window is set to the initial congestion window instead of 2.
So now that the DB files have been compiled and created, so we can transfer them to our AWS instances using SFTP. So this is the client, and we can see that I've transferred the DB files to this instance, and now we have to install them. So it's already been done, but these are the commands. So similarly, all these files have to be installed using this command. Now, after this has been completed, the files will be available in the boot directory. So let's go there and check there. So this is our image, boot image. So we can see after installing them using the command, these files will appear here. And now we got to go to the grub configuration file to make the changes. So when the system reboots, it's through the new kernel. So before that, let's cross check that it's running the old kernel right now. So this is the kernel that the system is using. So we got to go to the grub file to make the changes. We got to go down here and make the changes right here. So let's save the changes, and when we reboot, it should be from the new kernel. So now that the system has been rebooted, shown here, so we can see the kernel has been changed to our new kernel, 4.4.160 hash 3. So now the same steps should be followed on the server side. So again in the server, we can see our current kernel is this one, and we got to change it to the our custom one with the changes in TCP configuration. So again here the VM liners and the other files are already present in the boot. So we just got to make changes in the grub configuration file so we can boot through the new kernel, boot with the new kernel. So we can see we have the files. So let's just go and make the changes, the same changes we made in the client. So a small error, let's do it again. And that's it. So we gotta reboot the system so it will boot with the new kernel. Okay, so sudo reboot. So now that the server has been rebooted, so let's check if it's new kernel. So we can see our system is using the new kernel. So now this is done. Since the new kernel, we gotta set the roots again. So let's do that. Uh, this is the interface of the router, and that's 89. And this we gotta set the routes in the server side also, client side. Sorry. So let's ping the server. So now that the changes have been made, let's just try pinging the server from the client. So So we can see connection has been established. And now let's go to the router to make changes to the network parameters, that is 200 milliseconds delay and 20% packet loss. So let's set that. So first we'll set the delay and packet loss. And now in the ETH0 network interface. And now let's set the link capacity of 100 megabits per second. Now, now that the changes have been made, same changes have to be made in the server and client. And after this, we can do a SCP file transfer. Now that the changes have been made, we can start the SCP file transfer. But before that, we gotta set the congestion control to high blah and we know. So we're gonna do high blah first. Be this command. So the same thing has to be done in the server side too. Now after this, let's start our file transfer. So now this has started. The so the throughput will stabilize around 800 megabytes per second and 1 megabytes per second. So will be 8 this will be 8 mbps to 10 mbps when we convert to bits. So we can see with the high blah we have improved the throughput drastically. Before that, let's look at our SCP performance. So SCP, we can see in the same condition we're getting only 28 kilobytes per second. So this will be around 180 kilobits per second. So you can see the SAP performs really bad because of the congestion control. It thinks packet loss as congestion in the network and reduces the throughput unnecessarily. And we can also see the 3D graph. So we can see how throughput reduces with the increase in packet loss and delay. So we can see with 0% packet loss and even with increasing delay, the throughput was pretty stable at around 4 megabits bytes per second. But as packet loss increases, the throughput takes huge hits. This is because during each packet loss, uh, the the protocol reduces the sending window to half, or if timeout occurs, will send it to back to 1 MSS. So we can see SAP performance is pretty bad. But when we make changes to Hybla, as mentioned before, we get a better throughput. So we can see it's around this rate. So we can see for Hybla, we're getting around like 900 bytes per second to 1 megabyte per second. So this will be 8 to 10 megabits per second. So we can try TCP Vino next. Before all that, we made changes to the window sizing also. So we can see we have set the receiving window default size as 1.2 MB and receiving receiving window size to default as 1.2 MB. This is because our window or a bandwidth delay product is going to be 2.5 megabits. That's 100 Mbps into 200 milliseconds. So that's a bandwidth delay product. So we can choose our window sizes to be a large value because the network conditions allow it. So let's make the same changes in the server side also. Set it. Oh, sorry. So set it to Vino and let's try that. So in Vino, we're not getting a high throughput compared to Hybla. So chains in Hybla perform better when we compare it to Vino. So now that the AWS section is complete, Sahithi will show the TCP Hybla in VirtualBox uh, with the changes in TCP configuration, the kernel in the VirtualBox too.
After making the changes, we are trying to test this using the conditions that we have. That is, we have set 20% packet loss and a delay of 200 milliseconds. And currently, I have chosen the congestion control as Hybla. And this is, I'm transferring a file of 1 GB from the server to the client. And as you can see that the speed is around 1 megabytes per second, which is close to 8 mbps. Sometimes it's also increasing, so it's between 8 to 10 mbps. And let's wait for the final value that we get. So now the transfer is completed, and we can see that the final throughput is 1 megabytes per second, which is nothing but 8 mbps.